You ever notice how AI just seems to get it these days? Well, a huge piece of that magic is coming from a technology that has, kind of out of nowhere, become one of the hottest things in tech. We're talking about vector databases. And today, we're going to break down exactly what they are and why they matter.
I mean, let's just ask the question straight up. What kind of database is suddenly worth over $700 million? Databases, they're not typically the sexiest topic. They're the plumbing of the tech world. But right now, investors are pouring hundreds of millions into this one specific kind. So, what is going on here?
And trust me, this is not just hype. Just look at these numbers. Pinecone, one of the big names, just hit a valuation of over $700 million. You've got open source projects like Chroma raising $18 million. Weaviate, $16 million. This is a full-on gold rush. And in this explainer, we're going to figure out exactly why.
So, to get why there's so much excitement, we have to start with the fundamental problem they were built to solve. I mean, we already have databases, right? Why couldn't we just use the ones we've had for decades? Well, it all kicks off with this one, kind of staggering statistic. Over 80% of all the data in the world is what we call unstructured. Think about it. That's all the social media posts, the images, the videos, the audio files. It's messy, chaotic stuff that doesn't fit into the neat little rows and columns of a traditional database. And all that messy data creates this thing called the semantic gap. It sounds complicated, but it's really just the disconnect between how a computer sees data, as a bunch of pixels or a string of letters, and how we see it, with all its meaning, its context, its nuance. Here's a super simple way to think about it. You could have a photo with the tag sunset. A regular database can find that tag, no problem. But what if you wanted to find another picture that has a similar feeling? The same vibe, the same warm colors, but it isn't tagged. That's where the old systems just hit a wall. They search for keywords, not for meaning. So, how in the world do you bridge that gap? How do you teach a computer what a vibe is? This is where the big breakthrough happens. We figured out a way to translate that fuzzy human concept of meaning into the one language computers speak fluently: math. And the key to doing that is a concept called embeddings. So, a vector embedding is basically this. An AI model looks at a piece of data, an image, a sentence, you name it, and it converts the essence of that thing into a long list of numbers. That list of numbers is called a vector. Think of it like a numerical fingerprint for its meaning.
A perfect example is the word Apple. If you're talking about Apple, the company, the AI is going to generate a vector with high values for concepts like tech or business. But if you're talking about the fruit, you'll get a totally different vector with high numbers for things like food or sweetness. Same word, but the context creates two completely different mathematical fingerprints. It's pretty cool.
There's a really great analogy for this. It's like a party. You know how when you go to a party, people with similar interests just kind of clump together? The gamers are in one corner, the artists are in another. Well, vector embeddings do the exact same thing, just in a high-dimensional mathematical space. All the similar concepts, like apple the fruit and orange, they all get clustered close together.
Okay, so we've turned all our data into these points in space, and the similar stuff is all grouped together. But how does a computer actually measure closeness? What does similar really mean when you're just looking at numbers?
Turns out there are a few different ways to do it, and you pick the right tool for the job. You've got things like Euclidean distance, which is literally just the straight line distance between 2 points. Simple. It's great when the overall size or strength of something matters. But then you have cosine similarity, which is really popular for text. It completely ignores the distance and focuses only on the angle between the vectors. It's all about the direction of meaning, not how long the document is.
So now we can represent meaning, and we can measure similarity. We've pretty much cracked it, right? Well, not quite. We've just slammed into our next massive problem: speed. How do you possibly search through billions of these things in real time?
And I really do mean massive. We're not talking about searching a few thousand items here. Modern AI applications might need to sift through 1 trillion or more vectors. The scale is just immense.
If you tried to do this the slow way, the brute force way, you'd have to take your search query and compare it to vector number 1, then vector number 2, then 3, all the way up to 1 trillion. You'd be waiting forever. It is computationally impossible for any real-world app.
And this is the moment you realize why we need something new. Your standard, everyday database just can't do this. It wasn't built for this problem. We needed a specialized system, designed from the ground up for one thing and one thing only: speed. And that's what a vector database is.
The secret sauce here is a bunch of really clever indexing algorithms. Instead of that slow, one-by-one search, they use smart strategies.
For instance, some methods pre-sort similar vectors into buckets, so you only have to search in the most relevant bucket, not all of them. Others, like HSNW, build a kind of map of the data with express lanes that let your search jump almost instantly to the right neighborhood. Now, the core idea behind all these fast methods is called approximate nearest neighbor, or ANN, and it's all about one brilliant trade-off. They give up finding the 100% mathematically perfect match in exchange for finding a 99.9% good enough match almost instantly. And for pretty much every AI application out there, that trade-off is a no-brainer.
So let's put it all together. We can represent meaning, we can measure similarity, and we can search through it all at incredible speeds. This brings us to the killer app, the thing that's really driving that billion-dollar gold rush, giving AI a long-term memory. This technique is called retrieval-augmented generation, or RAG for short. It's a fancy name, but the idea is powerful and simple. You connect a large language model, like GPT-4, to an external brain, and that brain is a vector database filled with your own specialized knowledge.
So here's how it works. A person asks a question. The system turns that question into a vector and zips it over to the vector database. The database instantly pulls back the most relevant documents, maybe some internal company reports or product manuals. Then it bundles those documents up with the original question and hands it all to the LLM. So now the AI has all this extra, super relevant context to work with when it generates an answer.
And this is the real game changer. Suddenly, an AI isn't just a generalist that knows about the internet. It can become an expert on your specific data. It can answer questions about your company's financials, your project's history, anything. The vector database effectively becomes its custom, long-term memory.
What we're seeing here is the beginning of a shift away from generic chatbots and towards truly personalized, context-aware AI. And that leaves us with a pretty profound final question to think about. What happens when every piece of software, every application we use, has a perfect, searchable memory of every interaction it's ever had? The possibilities are, well, they're truly staggering.